This is Algebra 2, Lesson 13-4. We're doing exponential equations without logarithms. All right, so the general idea behind today's lesson is if you have an equation where I have 2 to the power of 3 set to 2 to the power of x, what is x? And hopefully most people can come to the conclusion that if the bases are the same, then these exponents must also be the same in order for this equality to hold. Therefore, x in this case is 3. So I'll say that again. Our general rule for today is if the bases are the same, then the exponents or the powers have to be the same. So I'll say the exponents here. So in general, this is what we're going to be doing. We're going to make sure that the left side and the right side both have a single base, and that base is the same. And then once we have the bases the same, then we can say then these powers must be the same. And I can set this 3x plus 1 equal to this negative 2x. And then we can solve for x. So let's give that a shot. Example 1 is already tricky right off the bat because I don't have the same base. I see I have a base of 3 and a base of 1, and this one doesn't have any exponents. So I have to choose a base. I can't change a 3 into a 1 without taking the whole thing to the power of 0, which you're not allowed to do. But I can take this thing and change it to a base of 3 and then make that one to a power of 0. Watch what I do here. This is going to be 3 to the power of negative 2n. I have not changed the left, but the right side is going to be 3 to the power of 0 because anything to the power of 0 is just 1. And now I have the same base, and I can set their exponents equal to one another, and I can now say that negative 2n, the exponent on the left, is equal to the exponent on the right, which is equal to 0. I can divide both sides by negative 2, divide by negative 2, and I get n is equal to 0. In example 2, I have 2 bases on the left, and I have a fraction on the right. I can tell that 6 squared is 36, so I'm assuming that my base that I'm looking for on the left is 6, and the base that I'm looking for on the right is also 6. So let's go ahead and combine our bases on the left using our properties of exponents. Whenever I have the same base and I am multiplying, I'm going to add the exponents. So I'm going to rewrite that left-hand side as saying 6 to the power of, I have a minus 1, and I'm going to add a 3a. On the right-hand side, I need to first flip this fraction. In order to flip it, I'm going to take this 36 and make it a power of a negative 1. And then from there, I'm going to change the 36 down into the 6. And that's just a fundamental rule, and this may be something that you want to write down in your things to remember section of your notes, that whenever you have a choice between making this number bigger or making this number smaller, always opt for making this number smaller. It's the easiest way to go. So from here, I'm going to not touch that left-hand side. It's still 6 to the power of, well, I guess I can reduce, right? I can say 3a plus a is a total of 4a. And this right side is going to be a 6. I need to have a 6 and a 6. In order to get 6 into a 36, I need to have this to a power of 2, and that's also to a power of negative 1. And when I have a power to a power, I multiply those powers, and my new equation is, okay, left side I'm not going to change. It's going to be 6 to the power of 4a minus 1. The right side is going to be 6 to the power of negative 2. Notice I have the same base, and I now can set their exponents equal to one another. And I can say that I have my exponent of 4a minus 1 on the left is equal to my exponent of negative 2 on the right, and I can simply solve. I can add 1 on both sides, giving me a 4a is equal to a negative 1, and then finally dividing by 4 on both sides to get a is equal to a negative 1/4. In example 3, I don't know what my base should be. I know that 16 squared is 256, but that is not this base over here. So again, it's one of those strategies that if I have the choice between making this number bigger or smaller, opt to make it smaller. So if I go down from here, I can make this a power of, I could do something like 2 to the power of 4, or I could say that this is 4 to the power of 2. Either one of these bases would work. And I noticed that 2 works for 64 and 4 also works for 64 because I happen to know that 4 to the power of 3 is equal to 64 on the dot. So you could have chosen a base of 2, but I think 4 is the fastest way to solve this problem. Let me show you what I mean. I know that if I choose a base of 4, I can turn the 4 into a 16 by taking it to the power of 2. This entire 16 is still to the power of negative 2n. On the right side, I also want a 4. I want to have the same base after all. That's my first step. And I know to convert 4 into a 64, I must take that to the power of 3. So this is going to be 4 to the power of 3, and this is still to the power of negative n minus 2. From here, I have both on the left and the right a power to a power. Whenever you have a power to a power, you multiply those, and this is now going to be 4 to the power of negative 4n. On the right side, I'm going to distribute my power 3 times a negative n and 3 times a negative 2, and this is going to be 4 to the power of negative 3n minus 6. Now, notice what we have. We have the same base, and we can now set their exponents equal to one another. Let's go ahead and do that to the right. I now can set negative 4n equal to my negative 3n minus 6. From here, I will add 3n on both sides, add 3n, add 3n, and that gives me a negative n on the left and a negative 6 on the right. From here, I'm going to divide both sides by negative 1, and I'm going to get n is equal to a positive 6. Our last example for the notes. This is one of the most disgusting types of problems I'm going to throw at you. I have things that need to be combined. I have a fraction that needs to be flipped. I have every single one of these a different number. You have to choose a common base with all of these. So for 8, there's no number squared that will give us 8, but there's a number cubed that will get us 8. Therefore, my base that I'm thinking of is 2 to the power of 3. If I choose a base of 2, can I get to 64? Yes. Can I get to 32? Yes. So the base here, the common base, is going to be 2. Let's go ahead and try it. So I'm going to have a 2 to the power of 3. That gives me an 8. And then I have to take this to the power of 2n plus 1. So this to the power of 2n plus 1. I also need this one to be a base of 2. If you're not sure how to get there, you can always do some scratch work and erase it. That's what mathematicians do all the time. 2 to what power gives me 64? We'll just do copies of 2 until you get there. So I'm just going to do way too many, and then we'll erase whatever we don't need. 2 times 2 is 4. 2 times 2 is 4. 2 times 2 is 4, and I happen to remember that 4 to the power of 3 is 64. 4 times 4 is 16, and 16 times 4 is 64. So that's how many 2's I need. I can erase one of these extra 2's. How many is that? That's 1, 2, 3, 4, 5, 6 2's. So it's 2 to the power of 6 is the thing that I'm looking for to get 64. Remember that I also need to flip this fraction so that the 64 comes and lives up in the numerator. To flip means I have a negative power, which means what I'm going to be doing here is this is going to be multiplying. Again, I have to copy this symbol, and it's going to be a base of 2. I need that common base, and it's going to be not a positive 6, but a negative 6. Again, just checking 2 to the power of 6 is 64. A negative will flip it into that 1 over 64. All right, now I need to work on the right side. By the way, all of this scratch work we can erase. In my class, I don't want you to erase this work. If you have some room to write this, leave it there. If you need that room for something else, you probably should have used a scratch piece of paper. For these notes, I want to be as concise as possible, so I will be erasing all of this work. To get 32, it is 64 divided by 2, which means it's one less copy of 2. Instead of a power of 6, it's a power of 5, and I can say that this is 2 to the power of 5 is 32. Again, this is still to the power of negative 2n minus 2. All right, again, I have a power to a power, a power to a power. That means I'm going to be distributing. When I distribute the 3 into this and the 5 into this, let's see what we get. I have 2 to the power of 6n plus 3 times 2 to the power of negative 6. And on the right side, I have 2 to the power of negative 10n minus 10. Notice I still have two different bases on the left. I need one base on the left, one base on the right, so I need to combine these. Whenever we multiply bases that are the same, I just add the powers. So I'm going to add those, and I'm going to get 2 to the power of 6n plus 3 minus 6. Adding a negative 6 is the same thing as just writing the negative 6 next to it. That's going to be equal to 2 to the power of negative 10n minus 10. Notice what we have now. We have a base that is the same, therefore their exponents also have to be the same. Let's go ahead and do that up here in the top right. So now I'm going to say 6n plus 3 minus 6 has to be equal to negative 10n minus 10. I can combine my like terms. I have a positive 3 and a negative 6 that just turns into a negative 3. So really this is a 6n minus 3, which is equal to negative 10n minus 10. And then from here, let's go ahead and move that 10n over, adding 10n to both sides, adding 10n to both sides. That means that this left side is reserved for my variables, my n's, which means this negative 3 has got to go. Let's go ahead and add 3, and then those will cancel, leaving behind a 16n on the left, and the right side I have a negative 7. Finally, we are going to divide both sides by 16, and n is equal to a negative 7/16, which feels like a weird answer. Maybe I made a mistake, but I'm not going to go ahead and question it until someone calls me out in the YouTube comments. That does conclude the notes for topic 13-4, exponential equations without logarithms. Thank you for watching.